In the previous lecture we have discussed the utility of the EK relation. We showed how from this relation we can obtain the crystal momentum of the electron. By differentiating it we can obtain the electron velocity called the group velocity, and by double differentiating it we can obtain the effective mass of the electron. We discussed the concept of crystal momentum in detail. Now in this lecture we are going to start a discussion of the energy versus distance diagram. Specifically we will discuss a quantitative model of a uniform semiconductor under equilibrium and non-equilibrium conditions. So we are going to discuss the EX diagrams or energy distance diagrams for various conditions. In this lecture we are starting with the uniform semiconductor because this is the simplest case that one can think of, and a discussion of the energy levels in this semiconductor will give you a good foundation for drawing the band diagrams for other more complicated cases. Let us look at some features of the EX diagram. An EX diagram reflects the spatial dependence of the following in a semiconductor. So when we are talking of a semiconductor, we are talking of a semiconductor volume, and actually the energy levels E can change as a function of x, y, z. However, in this course we will concentrate for most part on the one dimensional band diagram. We will have opportunity to introduce you to two dimensional band diagrams, but that will be only a small part of the course. So an EX diagram reflects the spatial dependence of the following. Firstly, the EK relation. In the previous lecture you have come across this EK diagram. Okay. Now we would like to see how this particular EK relation shown on this graph varies throughout the volume of the semiconductor as a function of position. Next, the EX diagram reflects the spatial dependence of electron concentration, hole concentration, and electrostatic potential, which are the parameters of the drift diffusion model. Now you already know that once you know NP and psi, you can also derive information about Jn, Jp and E as well. So although there are 6 equations in the drift diffusion model, these can be reduced to 3 coupled equations in Np and psi. So Jn, Jp and E are quantities that can be derived from Np and psi. Thirdly, the EX diagram reflects the spatial dependence of the energy levels associated with defects and impurities. Now when we talk of the spatial dependence of the EK relation, it is sufficient if we focus on these two energies, namely EC and EV. EC is the bottom of the conduction band EK relation, and EV is the top of the valence band EK relation. Once we know the variation of EC and EV as a function of position in the semiconductor volume, we can always build up the complete EK relation around these points. Let us begin with the EX diagram of a uniform semiconductor under equilibrium. So first we talk about the energy levels reflecting spatial variation of the EK relation. Here is the EK relation with the critical energies, namely EC and EV. We want to plot EC and EV as a function of x in the semiconductor. So within the semiconductor, EC and EV will be constant because the semiconductor is uniform and it is under equilibrium and therefore isolated from all other influences. So no electric field is applied across the semiconductor and no other fields. In fact, there is no electromagnetic field applied to the semiconductor, and therefore you expect the EK relation to be uniform, and therefore the EC and EV are constant with x. Now you can also show the entire conduction band energy width and valence band energy width, because the top of the conduction band is obtained from the top of the conduction band EK relation on this diagram here. Similarly, you can take the EK line corresponding to the valence band, it will have a bottom, and you can use that bottom point to get this energy and then get the bottom of the valence band. So EC and EV as a function of x reflect the spatial variation of the EK relation. We do not bother about the top of the conduction band or bottom of the valence band, because once you know EC and EV, you can always build up all other quantities. Now let us look at the energy level reflecting spatial variation of electrostatic potential psi or the electric field E. This energy level happens to be E naught, which is present in the crystal potential diagram. This crystal potential diagram actually contributes to these allowed bands and energy gaps. There is also another allowed band shown here, which is very thin, because this band is associated with electrons which are located close to the crystal atom. So this E naught, you recall from the previous lectures, is the vacuum level. That means it corresponds to an electron which has been moved from semiconductor outside into the vacuum, but it is touching the semiconductor surface. So that is the energy level E naught. So this E naught is shown as a constant line, and this E naught as a function of x reflects the spatial variation of psi or E of the drift diffusion model. It is shown as a constant line because there is no electric field applied to the semiconductor, it is under equilibrium, therefore there is no potential variation, and therefore E naught does not change. So if I move the electron on the surface along this line, it will not experience any change in the potential, because there are no fields within the semiconductor. Now why should the energy of an electron touching the semiconductor surface from outside in vacuum reflect the electrostatic potential? So suppose you have a semiconductor like this, and there is an electric field inside, then this electric field will cause a potential variation on the surface, and this potential variation can be sensed by the electron which is present here. You might ask, why not an electron inside? Will that not experience this electric field? Yes, this electron will also experience this electric field. However, this electron will also experience the effect of the atomic potentials. Therefore, we prefer to use an electron which is touching the semiconductor surface from outside, so that it experiences the electrostatic field alone because of space charges and so on, and not any electric field because of the atoms. The relation between the vacuum level E naught, which is an energy, and the electrostatic potential psi of the drift diffusion model is given here. So gradient of E naught by q is equal to gradient of minus psi. So in fact what this means is E naught by q is equal to constant minus psi. The negative sign comes about here because psi is the potential associated with the positive charge, whereas E naught by q is the potential associated with an electron which has a negative charge. So this relation is obtained just by integrating this. Now you can get the electric field as negative gradient of psi, which is nothing but gradient of E naught by q. So if you take the slope of this line, that should give you the electric field. In this case the slope is 0 because there is no electric field, because the semiconductor is in equilibrium So no external fields are applied, and since it is uniform, there are no built-in fields either. The E naught is an important energy which also serves as a reference while comparing electron energies in different isolated materials. Normally, we do not show the conduction valence bands and the crystal potential, etc., because it complicates the diagram. So what we do is we simply extract these three levels, E naught, EC and EV, in an EX diagram. Once we know the variation of these three levels as a function of x, we can always build up the other details about what happens to the energy conduction band, what happens to the valence band, what happens to the crystal potential as a function of x, what happens to the EK relation. Those can always be built up around these energy levels. Now let us increase the distances between E naught, EC and EV, because we want to show many more energy levels within these levels. So now the diagram is not to scale. Let us familiarize ourselves with these three levels, E naught, EC and EV, a little more. Consider an electron inside a semiconductor. What would be the energies associated with this electron? Now this electron, in terms of its energy, could be anywhere as shown here. For example, it could be in the conduction band, it could be in the valence band, or it could be in any of the lower bands which are present. Suppose the electron is in the conduction band and its total energy is as shown here with this particular location. Then the distance between the energy of the electron and EC, the energy level EC, is actually the kinetic energy. Therefore, EC is the potential energy of a conduction electron. Any energy higher than EC would imply presence of a kinetic energy. The difference E naught minus EC is normally represented using the symbol Q times chi. So chi is in potential dimensions, Q chi is energy, and this is called electron affinity. Now what is the physical significance of this difference? If there is an electron inside the semiconductor that is at the conduction band edge and it is just moved out into the vacuum touching the semiconductor surface, then its energy would change by a magnitude equal to Q times chi. An electron inside the semiconductor, if it changes its energy from the conduction band edge to the valence band edge, then it would undergo a change in energy equal to the energy gap. So EC minus EV is referred to as energy gap. A hole inside a semiconductor will be located in the valence band. So the kinetic energy of the hole is equal to the energy level EV, which is the potential energy of a hole, minus the energy of the hole. So this difference is the kinetic energy. So as the hole gains more and more kinetic energy, it moves down from EV. Now once we are familiarized with these levels E naught, EC and EV, let us now add more energy levels. First, we consider energy level reflecting spatial variation of electron and hole concentrations, or equivalently electron and hole current densities. Under equilibrium, this energy level is the Fermi level. EF as a function of x reflects the spatial variation of n comma p or jn comma jp of the drift diffusion model. Now let us see how does it reflect this information. Now these are the relations for Fermi level in terms of the electron and hole concentrations. So in terms of electron concentration, EF is equal to EC minus KT ln NC by N, where NC is called the effective density of states in the conduction band. And similarly, the same EF can also be written as EV plus KT into ln of effective density of states in the valence band divided by the hole concentration. So here we are reflecting this difference EF minus EV in terms of the hole concentration, and we are reflecting the difference EC minus EF in terms of the electron concentration. These relations you would have come across already in the first level course. Under equilibrium, normally the symbol for electron concentration is N suffix 0, and for hole concentration it is P suffix 0. So these are the two relations which connect the electron and hole concentrations to EF. Note that the same EF is representing both electrons and holes, because this is the situation of equilibrium. We will see later that in general in non-equilibrium, the EF associated with the electron concentration, called the EF suffix n or quasi Fermi level for electrons, is different from EF suffix p, that is the quasi Fermi level for holes, which reflects the non-equilibrium hole concentration. We also have another energy level E suffix I. E suffix I is the energy level corresponding to the Fermi level in an intrinsic semiconductor. So you already know what is an intrinsic semiconductor. It is a semiconductor which has no doping. Okay? Now you can say, why not call it pure semiconductor? So the difference between pure semiconductor and intrinsic semiconductor is that a pure semiconductor has no defects or doping, whereas an intrinsic semiconductor may have some defects and doping, but if it has doping, then its n type and p type dopings will cancel each other, so that the carrier concentration of this particular semiconductor, which is not pure, will be equal to the carrier concentration in a pure semiconductor. So an intrinsic semiconductor can be a pure semiconductor or an impure semiconductor whose carrier concentration is equal to the concentration in a pure semiconductor, because the acceptor and donor type dopings cancel each other. So in an intrinsic semiconductor, the Fermi level will be close to the middle of the energy gap. The reason why it is not in the middle of the energy gap is because Nc and Nv are different in general. So from your first level course, you would have known that the EI is given by EC plus EV upon 2 minus KT upon 2 ln Nc by Nv. For silicon, since Nc is more than Nv, it means the Fermi level in intrinsic semiconductor is a little below the middle of the energy gap. EC plus EV by 2 is the middle of the energy gap. Okay? Now the EI has the following utility. You can express the Fermi level as Fermi level with reference to EI. So in an n-type semiconductor, as for example the semiconductor shown here, EF is above EI, and therefore EF is given by EI plus KT ln N by Ni, and the same EF can be written in terms of hole concentration as EI minus KT ln P by Ni. Now how does the Fermi level reflect the current density? Now the formula for current density in the drift diffusion model is Jn equal to Q dn grad n plus Qn mu n into E. Now since this is a uniform semiconductor, EF is shown as a flat line and the semiconductor is under equilibrium, therefore there is no electric field, so E0, EC and EV are all flat, there is no slope because no electric field, and therefore uniform difference between EC and EF as a function of x reflects a constant electron concentration, and therefore grad n is 0. Similarly, we have already remarked that the electric field is 0 because E0 is flat, EC is flat, and so on, therefore Jn is equal to 0. So that is how flat EC and flat EF together imply a 0 electron current. Now the electric field acting on the electrons is given by gradient of EC by Q. So it is a gradient of EC by Q that reflects the electric field. Now you might say, why not gradient of E naught? Just now we had mentioned that the gradient of E naught is related to the electric field, electrostatic field. Now the point is, the gradient of EC and gradient of E naught are same in this particular case, because this is a semiconductor whose atomic structure is not changing with distance, and therefore even if you were to replace EC by Q by E naught by Q, your electric field would have been the same. However, strictly speaking, the electric field that comes into this location here for the expression for the electron current is the electric field experienced by a conduction electron. It is not the electric field experienced by an electron which is touching the semiconductor from outside, right? So E naught corresponds to the energy of this electron which is touching the semiconductor from outside, whereas the electric field in the Jn expression is the electric field acting on the electron in the conduction band, that is the electron inside the semiconductor but in the conduction band. Therefore the correct expression is, accurate expression is in terms of gradient of the EC by Q, which is the potential energy, which is the potential of a conduction electron. When we go to heterostructures where the composition changes with distance, the atomic structure changes with distance, then E naught and EC in general would not be parallel, and therefore a conflict will arise as to should you take the slope of E naught or should you take the slope of EC for the electric field on an electron in a semiconductor. So for a conduction electron you must use EC by Q. Now we are shortly going to give you an assignment in which you can show that drift plus diffusion current, both the terms can be compressed in a compact form as shown in this relation, n into mu n into gradient of EF. So the gradient of EF reflects both the drift as well as diffusion currents together. This compact form is very useful because it directly tells you how directly EF or gradient of EF reflects the electron current. Assignment will be given in a short time. Okay. Now let us discuss the current of holes, current density for holes following the same approach. This is the expression for hole current density, which you can write as shown here, where the electric field acting on the holes is represented by gradient of EV by Q. Because of arguments which are similar to the arguments given for the case of electron, the electric field acting on holes should be related to the gradient of the valence band edge. In a heterostructure, the valence band edge may not be parallel to the conduction band edge and may not be parallel to the vacuum level E naught, and therefore in such a situation it is important to note that the electric field in the hole current expression is given by the gradient of EV by Q, and you cannot use E naught here, nor can you use EC. Once again, in analogy to the case of electron current density, the hole current density can be expressed in terms of the gradient of the Fermi level. Since it is an equilibrium case, the same Fermi level is entering into the expression for holes as well as for electrons. Otherwise, as the assignment will show, what you will have in the expression for current density of electrons would be the quasi Fermi level for electrons EFN, and what you will have in the expression for Jp would be quasi Fermi level for holes, that is E suffix Fp. You can see here that since the Fermi level is flat, the hole current is 0, and similarly electron current is 0. So this is a very straightforward reasoning based on the gradient of the Fermi level for deriving the information about the electron and hole current densities. Now let us complete the picture. Let us show all the energy levels which reflect psi n and p, or E, Jn and Jp. So reproducing from our previous discussion, the E naught reflects the electrostatic potential psi. It also reflects the electric field E according to this relation. So we summarize by saying E naught reflects psi or E, and EF reflects N or P, or equivalently Jn or Jp of the drift diffusion model. So this is how the levels E naught, EC, EF and EV together represent the conditions in a semiconductor device, those conditions which are used in a drift diffusion model, and these levels are also useful to give you the spatial variation of the EK relation. Let us add now to this diagram energy levels reflecting crystal defects and impurities. The donor level corresponding to a shallow donor would be somewhere here close to the, in the energy gap, close to the conduction band edge. Now it is not necessary that the donor level should always be close to the conduction band edge. Only a shallow donor, that is that kind of a donor which gives you a large number of electrons in a semiconductor and converts the semiconductor into n-type, would be a shallow donor. Its energy level will be close to the conduction band edge. Example of this is phosphorus or antimony or arsenic in silicon. The positive sign here indicates donors because it means that when this impurity loses its electron, it is positively ionized. So a donor is one which gives an electron, right, and in process becomes positively charged. So that is why positive signs are used to indicate the donor level. Similar way one can show the acceptor level with negative signs. This is a shallow acceptor such as boron or aluminum in silicon. So it is located close to the valence band edge. Once again, an acceptor level could lie anywhere in the energy gap. A shallow acceptor would be close to the valence band edge. A trap level, apart from donors and acceptors, you can also have defects, and you can also have, apart from shallow donors and acceptors, other types of impurities which create energies near the middle of the energy gap. So either defects or impurities both can give rise to energies near the middle of the energy gap, and these are reflected here by this energy level called the trap level. It is called a trap because these impurities can actually physically trap electrons or holes. The distance between the conduction band edge and the donor level is referred to as ionization energy of the donor, and the distance between the valence band edge and the acceptor level is referred to as the ionization energy of the acceptor. For example, if you take this trap level, if it is acceptor type as it is shown here with negative signs, then its ionization energy would be the difference between ET and EV. If the same trap level was donor type, the ionization energy would be EC minus ET. The donor level, the acceptor level and the trap level help us determine EF. So these levels are useful in determination of EF. The trap level ET influences the Shockley-Reed-Hall recombination rate. In our earlier lectures we have discussed about Shockley-Reed-Hall recombination, and there you would recall we had used an energy level called this trap level. Now let us discuss how you determine EF and EG in a uniform semiconductor under equilibrium, including heavy doping effects. In the first level course, you would have determined EF in a doped semiconductor. What we want to do here is to slightly improve upon that formula and include heavy doping effects when the energy gap can decrease as compared to low doping, and Fermi-Dirac statistics, the Boltzmann statistics for electrons may not be valid, and you will have to use Fermi-Dirac statistics. So this is your energy level diagram relevant to this problem. The determination of EF starts from the charge balance equation, that is P naught plus Nd plus equal to N naught plus Na minus. You have come across this equation in the first level course. The suffix 0 indicates the fact that we are considering equilibrium condition. Nd plus is the concentration of ionized donors and Na minus is the concentration of ionized acceptors. Now this charge balance equation links electron concentration, hole concentration and Fermi level to the donor doping, acceptor doping, the donor level and acceptor level. Let us see how. Now we discuss the Joyce-Dickson approximation to the Fermi-Dirac statistics. According to this approximation, the hole concentration is given by Nv, which is the effective density of states in the valence band, into exponential of Ev minus Ef by kT divided by 1 plus 0.25 exponential Ev minus Ef by kT. The Boltzmann approximation is P naught equal to the numerator part of this expression. So this expression tells you that as your doping becomes heavy, acceptor doping becomes heavy, the EF will start moving closer and closer to the valence band, and in such a case this Ev minus Ef can become smaller in magnitude. Now Boltzmann approximation is valid when Ev minus Ef is greater than or equal to 3 times kT, or Ef minus Ev is greater than or equal to 3 times kT, or Ev minus Ef is less than or equal to minus 3 times kT. So this is your band diagram and this is your Ef, this is Ev, this is Ec. So as your doping becomes heavy, this starts coming closer and closer. If the Ef gets closer than 3 times kT, then you know that the Boltzmann approximation fails. Now that is where the Joyce-Dickson approximation becomes important. Okay? So the Joyce-Dickson approximation is such that for low doping it will reduce to Boltzmann approximation. You can see from here, when the doping is low, Ev minus Ef is really a large negative quantity, and therefore this denominator term simply becomes about 1 and you have only the numerator term. Whereas for example, when Ef becomes equal to Ev for heavy doping, in such a case P naught becomes equal to Nv by 1.25, whereas the Boltzmann approximation will only give you Nv. Okay, so there is a 25% error almost due to expression based on Boltzmann approximation when the doping is heavy and Ef is at Ev. A similar approximation exists for electron concentration, and it is given by N naught equal to Nc exponential Ef minus Ec by kT divided by 1 plus 0.25 exponential Ef minus Ec by kT. So when Ef is equal to Ec, the Joyce-Dickson approximation predicts N naught equal to Nc by 1.25, whereas the Boltzmann approximation, which is simply the numerator part of this expression, predicts only Nc. So there is a 25% error due to Boltzmann approximation when Ef is equal to Ec. The expression for Nd plus in this equation is given by Nd by 1 plus 2 times exponential Ef minus Ed by kT. This you would have come across in the first level course. So Nd plus is equal to 1 minus the fraction of occupied states at Ed into the total concentration of donors. Now this fraction is not given by the Fermi-Dirac function exactly, so that is why you put a dash. So Fermi-Dirac function would be 1 by 1 plus exponential of Ed minus Ef by kT. But when you are applying the function to impurity level, there is always a constant coming here. It is called a degeneracy factor, and that is why you use a different function than the Fermi-Dirac function. It is because of this factor that you have 2 coming in here. Na minus is similarly given by Na by 1 plus 4 times exponential Ea minus Ef by kT. Again this 4 is because of the degeneracy factor. So Na minus is nothing but Na into the fraction of occupied states at Ea. Finally, the energy gap is given by the energy gap for low doping and low temperature minus a change as a function of temperature minus a change as a function of doping. This is really referred to as the band gap narrowing because of heavy doping effects. Now the way this equation is solved is that first you solve for Ef and then you solve for electron and hole concentrations. Okay? So what you do is you take this expression, substitute for P naught, take this expression, substitute for N naught, similarly substitute these two things here for Nd plus and Na minus, and then solve for Ef. Now you might wonder, how do you solve for Ef when you have Ev and Ec, Ed and Ea also present there? So here what we need to do is you take any one energy as reference. Let us say if I choose to take Ev as reference. So in other words, all expressions which are in terms of other energy levels like Ec, Ea, Ed should be converted to energy level in terms of Ev. Let us see how. Supposing you have, for example, this expression Ef minus Ec. So you can write Ef minus Ec equal to Ef minus Ec plus Ev minus Ev. So add and subtract Ev because this is your reference. Now what will happen is this can be written as Ef minus Ev minus Ec minus Ev, and this is nothing but energy gap, and you have an expression for energy gap. In fact, we are shortly going to give you expression for energy gap. So that is how Ef minus Ec can be converted into Ef minus Ev. Similarly, supposing you want to convert Ed minus Ec, you want to convert Ef minus Ed into an expression consisting of the valence band. So Ef minus Ed. So you can write this as Ef minus Ed plus Ec minus Ec, that is equal to Ef minus Ec minus Ed, which you can identify as ionization energy of the donor. So that is why I will put a suffix D, because ionization energy of the donor can be different from ionization energy of the acceptor. So minus Ec. Now this minus Ec you can always convert it into Ev as shown here. So you can see Ef minus Ec was Ef minus Ev minus this. So I can write this part as minus this part as minus Ev minus Eg. So your Ef minus Ed is Ef minus ionization energy of the donor minus Ev minus Eg. So like that you can convert each expression into an expression containing Ef and Ev. Then you can solve for Ev minus Ef. Now the expression for energy gap is as follows. Let us look at the term that depends on the temperature. this is given by alpha times T square by beta plus T, where for different materials the constants have different values. So, for silicon the Eg naught, that is this term, is 1.169 electron volts. Alpha, its units are electron volt per Kelvin, it is 4.9 10 power minus 4, and beta has the units Kelvin, and it is 655. For gallium arsenide the values are 1.519 for Eg naught, 5.4 in 10 power minus 4 for alpha, and 204 for beta. So, alpha is of the order of 10 power minus 4 electron volt per Kelvin. Let us look at the band gap narrowing term for silicon. So, N stands for doping. It could be donor or acceptor. You have different expression for donor and acceptor. It turns out that for both donor and acceptor, delta Eg as a function of log n is close to a straight line, and therefore the form of expression is as follows: delta Eg as a function of Nd if you have donors, then it is equal to 18.7 into logarithm of Nd divided by 7 into 10 power 17, where this quantity Nd is in per centimeter cube, so many milli electron volts, for Nd greater than 7 into 10 power 17. Now, for Nd less than 7 into 10 power 17, this logarithmic term will become negative. It might give you a feel that the delta Eg becomes negative, which is not correct. So, for lower doping levels we assume delta Eg is 0. So, this formula is valid only for Nd greater than 7 into 10 power 17. So, this means in silicon for donor doping greater than 7 into 10 power 17, band gap will start narrowing. The formula for acceptor type case is as given here: delta Eg as a function of Na is equal to 9 times F plus square root of F square plus 0.5 milli electron volt, where F is logarithm of Na divided by 10 power 17, where Na is in per centimeter cube. So, evidently this formula is valid for Na greater than 1 in 10 power 17 per centimeter cube, and for lower doping levels delta Eg is assumed to be 0, because then logarithm becomes negative, which is not physically correct. So, here is an assignment for you: derive closed form relations in terms of Nc, Nv, Nd and E ion and temperature for electron concentration, hole concentration and Fermi level in an n-type semiconductor. So, you have to use the charge balance equation, the George-Dickson approximation, and the equation for concentration of ionized impurities. The simplification that will result here is that this is an n-type semiconductor, therefore you do not have to bother about hole concentration and ionized acceptor impurities. That simplifies an expression a lot, and it allows you to derive an analytical expression. If you want to do a calculation including Nd and Na in a general case, then you will have to resort to numerical calculation. The relations should work even for high doping levels, for which impurity ionization may be partial and Boltzmann approximation for the Fermi-Dirac statistics may break down. State the approximations made. There is another assignment where you use the derived expression for calculations. Using the above relations, estimate Np and Ef at 300 K in n-type aluminum gallium arsenide and silicon samples having Nd equal to 5 × 10 power 18 per centimeter cube and ionization energy of donor equal to 0.045 electron volts. Compare these results with those obtained using complete ionization and Boltzmann approximation. Here are the values of Nc and Nv for aluminum gallium arsenide and silicon. For aluminum gallium arsenide 4.7 × 10 power 17 per centimeter cube, and for silicon 2.8 × 10 power 19 per centimeter cube for Nc. And similarly for Nv, the values are 7.1 in 10 power 18 per centimeter cube for aluminum gallium arsenide and 1.8 in 10 power 19 per centimeter cube for silicon. Finally, let us discuss the Ex diagram of a uniform semiconductor under uniform volume generation. So, we want to show energy levels reflecting psi n and p of the drift diffusion model, which will also reflect E, Jn and Jp. Let us begin from the equilibrium condition, for which we already know the band diagram. It contains E naught, EC, EF, EI and EV. EF is above EI because the semiconductor is N type. Now when you shine light and there is uniform volume generation in this semiconductor, then everywhere there are excess electrons and holes, and the situation is depicted in the energy diagram by splitting of the Fermi level into electron quasi Fermi level and hole quasi Fermi level. It turns out that when the injection level is low, L stands for low level. When the injection level is low, the quasi Fermi level for electrons is same as or almost the same as the equilibrium Fermi level, the Fermi level under equilibrium, whereas the quasi Fermi level for holes moves significantly away from the equilibrium Fermi level. Now let us understand why. So using the concept of quasi Fermi level, EFN is equal to EC minus KT ln N upon NC upon N, and N is equal to N naught plus delta. And similarly for holes it is EV plus KT into ln NV upon P. P is equal to P naught plus delta. Excess carrier concentration is the same for electrons and holes. Now you can see from here, if N increases, this term reduces, which means the Fermi level goes closer to EC. On the other hand, if P increases compared to P naught, this term decreases, and according to this formula the quasi Fermi level for holes goes close to EV. So the same Fermi level now cannot represent both electrons and holes, because quasi Fermi level for electrons should go to closer to EC, whereas the Fermi level for holes should go closer to EV. Low level conditions, delta is much less than N naught. However, delta is always greater than P naught, because P naught is a minority carrier concentration in N type semiconductor. So this is very, very small. So generally the delta will be much greater than P naught, and therefore this quantity will significantly deviate from EV, because P changes significantly from P naught, whereas N remains close to N naught, because if delta is much less than N naught, N is N naught itself, and therefore this remains close to the equilibrium Fermi level. Now the carrier concentrations are therefore represented by these two formulae, which we just now wrote down on the board. They could also be represented using an equation in which the reference is EI for electrons and holes, rather than EC for electrons and EV for holes. Now if you increase the intensity of light, you can have high level conditions. High level conditions, there is a small change in the electron Fermi level, so it moves closer to the EC as compared to equilibrium, and the whole quasi Fermi level moves closer to EV also in a similar way. Now what happens in high level is that if I write the expression for high level for the same N type, then here delta is becoming much more than N naught, and anyway it is much more than P naught. So therefore in this case you have N approximately equal to delta and P approximately equal to delta. Both N and P are almost the same and equal to delta, and therefore if you put delta here and here, the difference between EC and EFN and difference between EV and EFP would be almost the same. They are not exactly the same because NC is slightly different from NV, okay? Otherwise they are almost the same. So therefore the high level condition is depicted by this situation. So this difference is equal to this difference approximately. Now let us complete the picture because we want to show psi also. So the electrostatic potential psi is reflected by E naught by q, and from this levels E naught, EFN and EFP, you can also get the electric field, the electron current density and hole current density. So these expressions are repeated from the previous slide. So in this case, for example, EFN and EFP both are flat, which means that electron current is 0 and hole current is 0. This is expected because electron and hole concentrations are uniform throughout the volume, therefore there cannot be any diffusion current, and there is no electric field within the semiconductor because it is uniform and no external electric field is applied, therefore drift current also is 0. So that is how Jn and Jp are 0. We can derive the information directly from slope of EFN and EFP. The electric field is obtained from the slope of E naught. Here is an assignment: current density in terms of quasi-Fermi level. Show that the current density of the drift diffusion model Jn equal to q dn grad n plus qn mu n e can be expressed in the compact form Jn equal to n mu n grad EFN using the relations n is equal to nc into exponential of minus Ec minus EFN by kT and E equal to 1 by q gradient of Ec, dn equal to kT by q into mu n. This is the Einstein relation. So you use these three facts and substitute these here, and you should show by algebraic manipulation that this equation containing two terms, drift and diffusion, reduces to a single term in terms of gradient of EFN. Derive an analogous expression for Jp in terms of EFP. When you derive the expression for Jp, you must use gradient of EV here instead of gradient of EC. We have already explained why you should not use gradient of E naught, because for using for the electric field term in the current density expressions, because in general in a heterostructure E naught, EC and EV all may not be parallel. So for conduction electrons you must use gradient of EC as the electric field acting on electrons. For holes you must use gradient of EV acting as the electric field acting on holes. With that, we have come to the end of the lecture. Let us make a summary of the important points. So in this lecture we have begun a discussion of the energy versus distance diagram. We explained that this energy versus distance diagram contains following critical energy levels. These are E naught, the vacuum level, EC, the conduction band edge, EV, the valence band edge, and quasi-Fermi level for electrons and holes EFN and EFP, which reduce to a single Fermi level EF in equilibrium. We also show the intrinsic Fermi level or Fermi level in intrinsic semiconductor in the energy band diagram because it proves as a convenient reference. We also showed how the energies associated with impurities can be shown on the energy band diagram. Basically, impurities and defects add additional energy levels within the energy gap. The E naught reflects the electrostatic potential and the slope of E naught reflects the electrostatic field experienced by an electron touching the semiconductor surface from outside. The Fermi level, the quasi-Fermi level for electrons reflects the electron concentration as well as the electron current density. The quasi-Fermi level for holes reflects the hole concentration and current density for holes. This is how the levels E naught, EFN and EFP together represent psi n and p or E, Jn and Jp of the drift diffusion model. EC and EV represent the variation of the Ek relation throughout the semiconductor volume. Finally, we have mentioned that the electric field in the expression for current density for electrons should be expressed in terms of the gradient of the conduction band H, because conduction band H is the potential of electrons in the conduction band, and the electric field term in the expression for hole current density should be expressed in terms of gradient of the valence band H, because valence band H is the potential energy of holes.